Thank you very much for the introduction, and it's a pleasure to be here, and thanks for the invitation. So we are still on solid-state qubits. Now we're back at the optical frequency. I'll tell you about photon-emitter interfaces. I'm from the Niels Bohr Institute in Copenhagen, University of Copenhagen. So let's see. Yeah, so solid-state quantum dots, that's a platform that I will be talking about now. And so it's quantum dots embedded in photonic nanostructures. Quantum dots are solid-state emitters. We can have spins inside these quantum dots. We can have them as two-level systems. I'll talk a little bit about each. We put them inside these photonic nanostructures. Our specialty is planar photonic crystal waveguides, in particular, to enhance light-matter interaction. And of course, I'm not implying that we are the only ones doing this. There's a whole community doing this, and there are many different solid-state platforms, molecules, and there's a lot of atom physics and so on. I'll only be talking about the quantum dots here. I would say there are potentially two different implementations. There's a planar and the vertical structures. And it's the same type of physics. So in particular, Richard Warburton Basel is pursuing that platform, but many others as well. And I won't cite all the literature at all here in this talk, but if you're interested in some kind of review, you can look up this Physics Today paper, recent one. So figure of merit, I think I don't need to say much about that for the audience here. So it's very much about the coupling efficiency, beta factor, we call it in optics. It's the probability that we couple single excitations from the quantum dot into a propagating modal waveguide. It can be really large in these structures due to the photonic band gap effect here. Well, that's a figure of merit for a source of single photons, if you want a deterministic train of single photons, as this figure illustrates. But it's also linked to the quantum cooperativity by this simple formula. But only if you have no decoherence processes, this formula holds. So, of course, the name of the game is also to reduce all decoherence processes, charge, noise, phonon, contributions, nuclear spin coupling. There are all kinds of different processes that play a role here. And it's really quite some reasonably new news on this platform that we start to have atomic physics kind of behavior for solid-state systems, so for solid-state quantum emitters. It's a non-trivial thing. So then we can really start to do real quantum optics experiments on this platform. And what's the secret in order to get that? Well, it's not a secret, but what's a weapon? I mean, you embed these quantum dots inside PIN heterostructures and applying an electric field across these quantum dots. And that really does a great job in cleaning up the environment, because charge noise, electrostatic fluctuations in the vicinity of the quantum dot will stark shift the quantum dot, and you need to overcome that charge noise. And of course, that also enables you to tune the quantum dot levels a little bit by applying this electric field. And finally, it allows you to do spin physics, because now with the heterostructure here, you can start to tune in, tunnel in single electrons or single holes inside the quantum dot and do spin physics in this system. So these electrical contacts make them of high quality, low leakage noise. I mean, a lot of device stuff going on in order to get that to work. That's really key for the things I'll be talking about here. So how do you quantify the amount of noise? One experiment you can do is just similar to the fantastic experiments we saw in the previous talk. I mean, you do transmission type of experiments through a quantum dot in a waveguide, and you see these extinction dips over here when you're hitting the resonance of the quantum dot. And it's always tough to come after the supernova qubit talks, but we're proud about these. We see, 80, 85, 90% extinction dips. That's pretty good at optical frequencies. And we go in, of course, and look at the narrow line width here and analyze this line width and compare it to the radiative emission time from the decay dynamics to see how close am I to the transform limit. And this is all the statistics that you see here. We don't need to dive into all the details, but just a typical number here would be like, less than 15% residual noise. And this is a continuous wave measurement. So this is really taking a narrow band laser and shine it through through the waveguide, look at the transmission through the waveguide, seeing this extinction dip, you are sensitive to any noise processes on any time scales, both the slow spectral diffusion drift, the faster phonon decoherence processes, and so on. So it's really a very, very sensitive test of the line width of the system. And again, just to emphasize, I mean, getting that kind of performance in nanostructures, the membranes are 180 nanometers thin, so the quantum dots are very close to surfaces. So it's not trivial that you can overcome all these noise processes. So with such a platform, we can start to do various type of experiments. We already heard about these photon nonlinear processes. So that would be a single quantum dot with high coupling efficiency scatters off a single photon with a high efficiency. So if I take two and scatter it off a two-level system, well, then I get quantum dot can only scatter one photon at a time, right? I mean, even a single photon saturates the quantum dot, so there'll be a preferred probability to be transmitted past the quantum dot. So you'll see some quite pronounced photon bunching effects if I'm measuring the photon statistics of the transmitted light. You'll see the single photon component being reflected with high probability. That's these extinction dips. And then you'll see the two photon components have a preference to be transmitted past the quantum dot, meaning that you'll see bunching in the G2. So this is a photon nonlinearity, something that does something different when I send in one photon and two photons. It's a particular type of nonlinearity because it really distorts the photon pulses. I mean, you don't have just undistorted pulses passing through. This two photon scattering process distorts the pulses by the interaction with the emitter. So we have been thinking about what can you possibly do with that kind of nonlinearity. And here's some work together with Klaus Møllmer, my colleague, and in Copenhagen, about trying to make use of this photon distortion in a clever way to do photon sorting. Now we're actually in the chiral setting, like in the previous talk, theoretical proposal, because this is a quite nice and experimentally simple operation, right? I just use a two-level system here in this case to scatter photons just passively. I don't need any active control on the quantum dot. I just use them as passive scatters. So if I can use that to do photon sorting, well, what is my control knob? My control knob is I can control the pulse duration and shaping the pulses that I'm sending into the quantum dot. And here's a proposal of how, if I come in with a superposition of one and two photons, I want to then control this pulse in such a way that I scatter those photons into orthogonal spectral temporal modes, because then I can sort them subsequently. And that is a numerical analysis of what's the fidelity of that photon sorting, that transformation that you can achieve if you're shaping the pulses. And with a single emitter, I think you can get about 90+% fidelity. Even with two emitters, you can get remarkably close to the perfect fidelity, 99.97% fidelity, which is a totally non-trivial thing. I mean, you're distorting these pulses at the first emitter, but you distort again at the second emitter in such a clever manner that you end up in almost perfect orthogonal spectral temporal modes. So if you have them in orthogonal spectral temporal modes, then you can do things like frequency conversion, for instance, to deterministically select the one and two photon components. This is work, for instance, what they do in the Silberhorn group in Paderborn. They're using these spectral temporal modes as alphabets for quantum information. And they're doing frequency conversion you're using frequency conversion to select these spectral temporal modes. So this would be our photon sorter proposal. You're scattering off one or two-level systems. You're doing some frequency generation, and you're using a local oscillator to select the spectral temporal mode you're interested in, converting, for instance, the one photon component, even the two photon component untouched, and then you can rip them apart by a beam splitter. So here's some recent experiments along these lines where we're really demonstrating this pulse control and the change of the quantum correlations when we're controlling the input pulses and scattering off a two-level system. You see these extinction dips again. You see the G2 in the transmission. These are already quite some more data. I think we have like a few hundreds of D2 in the transmission nowadays. So it really, again, the very sensitive to the decoherence processes. And then in an experiment here, we are measuring the dynamics of the D2 in the transmission past the quantum dots here, where we are comparing subsequently reflected photons. So this is one photon being reflected and one photon being reflected in the next pulse. You're looking at the correlations in that case. This is time. That's D2 as a function of T1 and T2. So it's a time map of the D2 function. And here we are looking at the two photon processes, where the two photons are to a very large extent, when making the pulses long, you see that they are highly correlated in time, meaning that these photons are really transmitted in pairs. And you can extract this quantum correlation also as a function of pulse duration and see that you can really get a strong correlation by controlling this pulse. It turns out you can actually also do energy time entanglement, so this is work on the way we'll come out with very soon, that these kind of correlations will actually also allow entanglement, even violating a Bell inequality from these two photon transmitted processes. Okay, so that was two photon nonlinearity kind of work. I already promised you, and it's a spin conference, so I promised that we could have a spin inside the system. So let me say a little bit about that. Again, we nicely experimentally control that by this bias across the quantum dots. So just dialing in this bias, you get to a regime where you have a ground state of an electron, for instance, so it can be a hole that you're tunneling in, and then you have a free level energy system like that, where major stable ground state that you can start to do spin tricks on. So this is a proposal of how you can use that level system to produce multiphoton entangled states. It's originally a proposal from Lindner and Rudolph for some years ago, but it's very, very well suited to the quantum dot platform, because what we are very good at with quantum dots is really to produce photons quite rapidly of high quality. What we are less good at is keeping the information, we have a lousy coherence time, so we want to emit the photons very, very rapidly. And probably other things we are bad at, but we are good at producing photons. So this is a proposal where you produce photons very rapidly. So it works as follows. I mean, you're preparing this spin state in a coherent superposition state with applying a pi/2 pulse, spin rotation pulse, to prepare this superposition state. And then you're running a pulse sequence where you're exciting the quantum dot if it's in a spin-up state, and then it will emit a photon in an early time bin. If it was in the down state, it won't emit any photon. There's no excitation of this transition. Then you do a pi rotation of the spin, and you repeat it. So you're exciting and emitting a photon in a late time bin. And again, I started in a superposition state, and I do spin rotations in between the pulses. So if you do that, you're really ending up with a multiphoton entangled state, like what is shown here. So this is GHZ state. Spin is pointing up. Photon 1 is emitted in an early time bin. Photon 2 as well. Photon 3 as well, and so on. If the spin is down, all the emitted photons are in a late time bin. So this is entanglement, multiphoton entangled state, where the quantum dot is entangled with all the spins. The quantum dot spin is entangled with all the photons, but there's also entanglement in between the photons due to all these spin rotations that we are doing. And that's a GHZ state. It could also be a cluster state, so I could choose to do either a pi rotation in the pulse sequence with a pi rotation or with a pi/2 rotation, and there I'm really either generating a 1D cluster state or a 1D GHZ state. So there's quite some flexibility in the spin control that allows you to generate interesting entangled states. So nice and simple. How well does it work in practice? Well, one point I should make is that in this sequence here, there's actually a spin echo pulse in between the excitation and emission. And that's key. That's a key thing, because one of the things we are, as I said, pretty bad at this on this platform is to keep the spin coherent. Spin coherence times is 20, 30 nanoseconds or something like that. Really, really lousy. But I don't need anything It's actually not the limiting factor of this protocol at all, because I do a reshaping here in between, and the T2 time is significantly longer. Yeah, and I can do these spin rotations fast. So what matters is actually how fast do I do these spin rotations relative to T2 star for the fidelity of the protocol. So we worked out the fidelity or the infidelity of this entanglement of this n-photon state, work done with my amazing colleague Anders Sørensen and his theory group. And really, lots of details here, but really included all the physical infidelity mechanisms in the system. There's a finite indistinguishability of the photons that has to do with coupling to phonon bath. There's a fourth level, and you need to be detuned away from this level, otherwise you will end up in the wrong state, and that depends on the magnetic field and the G factors of the electrons and so on. And then there's an important parameter that is called, we call it this branching ratio, B. And that is because I want to do two things at the same time. I want to excite and emit on this transition. I want a cycling transition here to get the photons emitted. I don't want to decay on this transition, because then I lose the excitation out of the system. On the other hand, I don't want to shut this transition totally off, because we want to do these spin rotations, and these spin rotations are done optically by Raman pulses that drive this transition. So I want to both be able to cycle and do spin rotations, and for that reason I want this branching ratio to be large but not infinite. And it turns out in photonic crystal waveguides you naturally have this asymmetry between the transversely polarized transition, which would be that transition, and a transition like that along the waveguide, which would be this transition. The asymmetry of the waveguide naturally gives a large branching ratio, which is the key parameter in the infidelity. So if you put in numbers here, we get, like for real experimental numbers, down to 1.6% error per photon, which you can say, okay, is that good or bad, or is it promising or not? What should I compare it to? I mean, the ultimate thing you could compare it to is to say, maybe I want to build fault-tolerant quantum computer, optical quantum computer. Based on that, what are the thresholds for fault tolerance? And that is about at the 1% level. So at least it starts to smell like something. And those are not just fantasy parameters we are plugging in, it's real experimental parameters. And once you know that, of course, you also can think about ways to tweak them and get even better. So I think this is quite interesting. And maybe just a few words about how would you then possibly build a quantum computer based on this, if that's what you want. Well, what you would do is to take, have the quantum dot emit 5 photons or 10 photons, and then you will route them off to a waveguide, and then emit 5 or 10 photons again, route them to another waveguide, and so on. Build up your resource like this, and then do linear optics, which are probabilistic gate entanglement operations that are very, very cheap in optics to do, because that's just linear optics operations. But that's actually a way of creating, universal quantum resources, even with one quantum dot potentially. In reality, we want to take more, and we can discuss this in much more detail if you're interested. Okay, so experimental demonstration of this multiphoton entanglement, this specific protocol with the time-binding coding that we talked about. These are our recent data. So far, we are at the spin-photon and spin-photon entanglement level, so it's up to 3-qubit entanglement, limited and gradually progressing. I mean, these are really work that is gradually becoming better and better. Particular this implementation here, and a technical thing that we can apply a large magnetic field so that you actually have the high indistinguishability of the photons being emitted as well, while previous works by other groups have been working in either zero magnetic field or very low magnetic field, where you don't have this indistinguishability. And that's key for the reason I just said. Eventually you want to take these cluster states and chop it up and interfere them with each other to do to grow larger quantum entangled states. There's another opportunity that we looked a little bit into, and that is to use, instead of having the spin and the quantum dot emitting a photon, you could have it scattering a photon. So in this case, we prepare a photon in a superposition state of 2 time bins, an early and a late time bin, and you scatter it off a spin that is in the superposition state. And you get spin-photon entanglement in that case as well. In this case, heralded on a photon being reflected from the quantum dot. So this is not a deterministic source, unlike the emissions source I was talking about before. There we start with a pi pulse putting the quantum dot in the excited state, and it emits deterministically a photon. Here, scatter probabilistically a photon. But there can be some interesting trade-offs and opportunities here where you're sacrificing determinism for higher fidelity, yeah, it's still not at the level of what I promised you, but this is like a 74% fidelity level at the moment for this specific implementation, but still improving, and I think we know how to improve this further. So where is this all going? Well, one thing that is really, really interesting to do is to start to scale up. So far, I spoke about just a single quantum dot, either with or without a spin in a waveguide. Scaling up to multiple quantum dots really allows you to do quite advanced things. So this is a very nice theoretical proposal from Sophia Economics Group in the US, where they propose how to generate really advanced entanglement structure by having two coupled quantum dots, where one quantum emitters, where one emitter is emitting the photons and the other emitter is doing gate operations on the emitting quantum dot. So then you can, this is like a quantum repeater type of state you can start to synthesize. So the step going from 1 to 2 is quite a significant step in terms of the complexity of the states that you can generate. Yeah, so that's a hard one for us, so to scale up to multiple emitters, because quantum dots are different. You need local control to tune them into resonance. There's also a spatial dependence on stuff where the quantum dot is sitting, the spatial dependent decay rate, and so on. So this is a recent experiment where we showed the coupling of two quantum dots, superradiant, subradiant effects in these photonic crystal waveguides, exciting one of the quantum dots and seeing both the sup and subradiant feature in the decay dynamics. And I see I'm running out of time, so maybe I'll just say a little bit about the quite advanced, if I may, devices that we can make nowadays. Again, this planar platform gives you quite some opportunities to locally isolate electrically also quantum dots, so that you can do local tuning of individual quantum dots. So this is a device where we have two quantum dots sitting in each waveguide. It's on the same chip. They're excited by the same grading here that is distributed to the two quantum dots. We have local electrical tuning on each of the quantum dots, so you can tune them into resonance and do, in this case, homomental interferometry. And why can I do it individually, this tuning? Because we can trench the device so that the P layer is trenched so they're electrically isolated. And that can also be applied in these in a single waveguide where we'll have two quantum dots electrically isolated, so we can use dark tuning to tune them up. So I think that's really our scaling up architecture. It's tedious to scale 1, 2, 3, 4, but you can do a lot with that scaling because, again, we emit these many photons. That's a relatively cheap resource on our platform. So with that, yeah, I come to the conclusion. I just thank the group at the Niels Bohr Institute. I would like to thank my colleague Leonardo. He's a wizard of all the devices. Anna Sørensen, he's a wizard of all the theory. And Arne Ludwig, he's growing all these wonderful materials that we apply. Thank you very much.